Okay, so in this section, we're going to talk about inner product, length, and orthogonality of the vector spaces. So the goal of this section is to know the geometric concept of all these things. So basically, we already know the concept of length, distance, and perpendicular in R2 and R3, and we want to extend these ideas for R to the n-dimensional usual vector space. So let's suppose that U is the vector in Rn, then we consider the vector as n by 1 matrix and define the transpose as 1 by n matrix. Then the matrix product U transpose times U is a 1 by 1 matrix, which are very similar to the scalar. So we are going to write that as a scalar without bracket. So let's see some example about this one. So suppose that you have U equals to 1, 2, and 3. Then U transpose times U is, well, you have the matrix 1, 2, 3, and the column vector 1, 2, 3. Then if you multiply these two, then this gives you 1 squared plus 2 squared plus 3 squared, and this equals to 14. So similarly, if you have V equals to say 1, 0, negative 1, 1, and 3, then we can calculate V transpose times V as 1, 0, negative 1, 1, and 3, multiplied by 1, 0, negative 1, 1, and 3. And this equals to 1 squared plus 0 squared plus negative 1 squared plus 1 squared plus 3 squared. That gives you 9, 10, 11, 12. So suppose that U and V be vectors in Rn, that the scalar U transpose times V, or we simply write U dot V, is called as the inner product or dot product of U and V, and U dot V is defined by U transpose times V, which is given by the vector U as a row vector and the vector V as a column vector. And if you multiply them literally, then that gives you U1 V1 plus U2 V2 and so on plus UN Vn. So if you already had the calculus 3, then this is the same as the dot product in the calculus 3. So there are some algebraic properties for the dot product. So suppose that you have U, V, and W inside R to the n and C to be a scalar. Then we have U dot V equals to V dot U, so the dot product is commutative. And if you have U plus V dot W, well, then this equals to U dot W plus V dot W. So basically, we can distribute W into the parentheses, and C times U dot V equals to C times U dot V. And that is again the same as U dot CV. So we can factor out the scalar or push the scalar into the parentheses. Or in other words, the dot product commutes with the scalar multiplication. And if U dot U is positive and U dot U equals to 0, well, in that case, we have U equals to 0. So basically, if you apply B and C simultaneously, then C1U1 plus so on plus CPUP, dot product with W equals to, so you can first distribute W into parentheses and then factor out the coefficient. Well, that gives you C1 times U1 dot W plus so on plus CP times UP dot W. So you can use this to calculate the dot product a little bit easier. So suppose that you have U and V and W in this way, and we want to calculate U plus V dot product with W. So basically, well, this is the same as U dot W plus V dot W. So here, U dot W equals to U transpose times the vector W. Well, this gives you negative 102 times 0, 1, 3. And this gives you 6, I guess. And similarly, this equals to V transpose times W, that equals to 5, negative 1, and 1 times 0, 1, 3, and that gives you negative 1 plus 3, which equals to 2. So we can tell that u plus v, the product with w, equals to u dot w plus v dot w. That equals to 6 plus 2, which is 8. So you can make use of zeros as much as possible. The length or the norm of v is the scalar defined by the square root of v dot v. Or if you calculate v dot v, you get v1 squared plus v2 squared and so on plus vn squared. So this actually extends what happens in R2 and R3. The magnitude of a vector is the same as the square root of the squares of each entries, and this is exactly what that is. And if you take the square for the both sides, then we get the magnitude squared equals to v dot v, and a unit vector u is the vector of its length equals to 1. And for any given vector v inside Rn, and if you divide by its magnitude, then you get a unit vector in the same direction as v. So for example, suppose that v is given by negative 1, 2, 0, and 3, then we can calculate the magnitude of v as the square root of the squares of each entries. So it's negative 1 squared plus 2 squared plus 0 squared plus 3 squares. And this equals to square root of, I guess, 1 plus 4 plus 9. And this equals to square root of 14. So if you normalize the given vector, or if you divide the given vector by its magnitude, then we get a unit vector which has the same direction with the given vector v. And one thing to observe is, well, for any scalar c, if you scale a given vector, then that actually scales the magnitude of the given vector. So intuitively that is really clear. But if you prove that the magnitude of CV equals to the square root of CV dot product with CV, but we can factor out C outside of the dot product, so we get C squared times V dot product with V, where we get the absolute value of C, square root of V dot V, where this equals to the absolute value of the magnitude of V. So this way we can factor out the scalar outside of the magnitude of the given vector. The distance between two vectors in Rn is defined by the magnitude of u minus v. And if you expand this to each entries, then this equals to the square root of square sums of each entries. So this gives you u1 minus v1 squared plus u2 minus v2 squared plus so on, plus un minus vn squared. So this again generalizes the distance formula in R2 or R3. So for example, if you have the vector u and v's in this way, we have u minus v equals to 1, 4, 2, 0 minus negative 2, negative 1, 1, and 3. And this equals to 3, 5, and 1, and negative 3, I guess. So the distance between the vector u and v equals to the magnitude of u minus v, which is the same as the square root of 3 squared plus 5 squared plus 1 squared plus negative 3 squared. And this equals to, I guess, 9 plus 25 plus 1 plus 9. So this gives you 10 plus 25 equals to 35. So this equals to square root of 44. Okay, so let us talk about the orthogonal vectors. We can observe that two lines are geometrically perpendicular if and only if the distance from u to v is the same as the distance from u to negative v. So let us draw the picture of this one. So if you have a vector u over here, And let's say this green one to be vector v, and this one to be the opposite of the vector v. Then we know the fact that these two lengths are the same if and only if the angle between v and u are 90 degrees. And this is one property of isosceles triangle. So if you measure the distance between these two vectors, and this has to be the same as the distance of u and minus v, or by definition, we have the magnitude of u minus v equals to the magnitude of u plus v. So if you take the square for the both sides, then this gives you u1 minus v1. So let's assume that your triangle is in R2. Then that gives you u2 minus v2 squared equals to u1 plus v1 squared plus u2 plus v2 squared. Then the left hand side becomes u1 squared minus 2 times u1 v1 plus v1 squared plus u2 squared minus negative 2 times u2 v2 plus v2 squared, and this equals to u1 squared plus 2u1 v1 plus v1 squared plus u2 squared plus 2 times u2 v2 plus v2 squared. So now we can cancel out u1 squared, v1 squared, u2 squared, and v2 squared. And if you move these two on the right hand side, then you get 4 times u1 v1 plus 4 times u2 v2 equals 0. Or in other words, we get u1 v1 plus u2 v2 equals 0. Or equivalently, we have u dot product with v equals to 0. You can apply the same argument for Rn, but you will have n number of squares in this part. So, two vectors u and v's are orthogonal if and only if the dot product u and v equals to 0. And if you use this, we can tell that the 0 vector is orthogonal to every vector in Rn. And this is because if you take the dot product with 0 vector, then this equals to u transpose times the 0 vector. And whatever you multiply 0 into, you will get the 0 vector. So 0 is orthogonal to every vector in Rn. And two vectors, u and v's, are orthogonal if and only if the magnitude of u plus v squared is the same as the magnitude of u squared plus the magnitude of v squared. And this is in fact the Pythagorean theorem. So if you build a triangle using u and the vector v, then we get u plus v over here. So we get the right triangle if and only if u plus v, the magnitude of this one squared, is the same as the magnitude of u squared plus the magnitude of v squared. So far, we have seen some algebraic properties of orthogonality. So now we're going to see some geometry of it. In R3, we know that the z-axis, like any vectors of the form 0, 0, c, is orthogonal to the xy plane. So for example, if you let this vector equals to u, then we have u over here. And this vector is orthogonal to xy plane. So let's say W be the vector space spanned by 1, 0, 0 and 0, 1, 0. So it is the xy plane. Then U is orthogonal to all the vectors in W. So we say the orthogonal complement W to the perpendicular equals to span of 0, 0, 1. So the orthogonal complement of W is a collection of all vectors in Rn, which is orthogonal to the given vector space W. Or in other words, we can write W perp, so we call W perp as W perp that stands for the perpendicular. So it is set of all elements such that if you take the dot product for any vector w in W, then you will get 0. So here are some facts about W perp. We have W perp is a subspace of Rn, and this is because the orthogonal complement can be written as the span of some vectors. And we can verify X is an element of W perp by checking whether X is orthogonal to every vector in a spanning set of W. Now, suppose that you have A as an n by n matrix, then the orthogonal complement of the row space of A is the same as null space of A, and the orthogonal complement of the column space of A is the same as the null space of A transpose. So you want to note that we have null space inside the domain of the given matrix, R to the number of columns. So the row space of A sits inside the Rn as well. And if you switch the rows and columns, then we get null space of A transpose sits inside R to the M, or the column space of A sits inside Rm as well.